frequency behavior of single-time constant networks. Hello everyone, my name is Rafael, I am an electrical engineer, and in this video I would like to debate with you the frequency response of single-time constant networks, and to do so I chose this exercise. I am going to read the problem and show you the solution. Frequency behavior of single-time constant networks. Find the transmission, the corner frequency, the transmission at DC, and the transmission at f equal to 2 MHz for the low pass STC of the following circuit. Okay, this is the question, and let's do it. Letter A, we are going to find the transmission. Okay, to find the transmission, we have to correlate the input voltage with the output voltage. Let's do it. We're gonna have a current here. We're gonna have a current here, and we're gonna have a current here. All right? And we can do this. We can write that the input voltage minus the output voltage divided by this resistance is this current here. And how about this current? This current can be expressed as the output voltage divided by this resistance. And how about this current here that goes through the capacitor? It is the division between the output voltage and the capacitive reactance. All right? Did you get it? So let's move on. We are going to separate this. VI divided by R is going to be equal to V0 divided by R plus V0 divided by R again, because we have V0 divided by R here, and we have V0 divided by R here. And here we're going to have SC times V0. Okay? We are going to put it in terms of V0, and we get that VI divided by R is equal to V0 1 over R plus 1 over R plus SC. Okay? Did you get it? Let's move on. We are going to do this. Let me erase it. Let me erase to get some room here. All right? I don't want to speak fast. I want everybody to understand everything. But we need to optimize our time. Then I don't want to make the video too long. Let's optimize our time here. VI is going to be equal to V0 times R, okay? And then we're going to find that R1 plus 1 plus SC, okay? We simply did some algebraic manipulations there to arrive at this. and then we can cancel this with this. Alright? And ultimately we find that VI over, okay, VI is equal to V0 times 2 plus SRC. Alright? We are almost there. We are almost at the expression of transmission. What we need to do is to write it in this way. We have to write it in this way, V0 divided by VI, which is the transmission with respect to S. This is what we're going to do. T of S is then equal to 1 divided by 2 plus SRC. This is the transmission as a function of the complex variable. But for real frequencies, we are going to do this. S will be equal to JW for physical frequencies. Then the expression of transmission is going to then be equal to T of S equal to 1, 2 plus JWRC. Alright? Instead of writing S, we wrote JW. Okay. We are almost at the final expression of the transmission. I'm going to erase it here again, so you guys can fully comprehend what I'm doing. We are going to use that tau equal to RC is the time constant of the circuit, and W0 equal to 1 over tau equal to 1 over RC is the knee frequency, or the corner frequency. And we're going to substitute it here, and we're going to find that T of S equal to 1 over 2 plus J W over W0. This is the final expression of the transmission. This is what letter A wanted us to calculate. Alright? From this expression, we can calculate the rest. In letter B, the exercise wants us to calculate the corner frequency. What is the corner frequency, you may ask me? It is the frequency that the circuit start attenuating the signal. The circuit is going to start attenuating the signal at the corner frequency. Again, W0 is equal to 1 over RC. Okay? And we know that W is equal to 2 times pi times F0. Okay, this is the corner frequency that we're going to work with. The frequency at which the circuit starts attenuating the signal. And we're going to set this to be equal to each other. Okay, 2 pi F0, and then F0 is going to be equal to 1 over 2 times pi times RC. Okay? We are going to use these values here, 10 kilo ohms and 100 picofarads. We are going to substitute them here. So F0, the corner frequency, is going to then be equal to 1 over 2 times pi times 10 kilo ohms times 100 picofarads. Alright? Did you comprehend it? From this, I arrived at this. And if we conduct this calculation, we find that the corner frequency is equal to 159.2 kilohertz, approximately equal to this. So this is the response of letter B. This is the corner frequency, the frequency at which the circuit starts attenuating the signal. Now let's go to transmission at DC. This is letter C. Now we are going to calculate what letter C wants us to calculate. It is the transmission for DC. Transmission for DC. Letter C. Letter C is then going to be equal to transmission for DC. Okay? For DC, we know that the frequency is equal to 0 hertz. This is the definition of DC. And we had already calculated that the T of JW is equal to 1 over 2 plus JW divided by W0. Okay, here we can simply substitute this. As we know, W is equal to 2 times pi times F. If F is 0, then W is 0, alright? Do you guys get it? Then we know that transmission for DC is equal to 1 divided by 2 plus 0. Okay? And then we find that for DC, or at DC, this is equal to 0.5 phase 0 degrees. So what is the conclusion? The conclusion is that the output will be a half of the input with no phase shift. The output is going to be a half of the input with no phase shift. This is the conclusion. Now let's go to letter D. Letter D wants us to calculate the transmission for the frequency of 2 megahertz. Okay? In letter D, we are going to use the frequency of 2 megahertz. Again, we use the expression of transmission that we just found. Okay? But here, instead of using W and W0, we are going to use F and F0. Okay? You can calculate in your house yourself, and then you're going to find that this is the same. Okay? We already found F0, haven't we? We found F0 to be equal to 159.2 kilohertz. Hertz. And F, we want for F equal to 2 megahertz. We can simply substitute these values here and we find the transmission equal to 2 plus J, 2 megahertz divided by 159.2 kilohertz. Okay? And then we find that this is going to be equal to 2 plus J, 12.56. Okay? Up to this point, so have you guys understood everything? If yes, we can go ahead. We can go ahead and continue our calculation. Okay, and this is the transmission that we just found. For F equal to 2 megahertz. Okay? Now we are going to analyze the magnitude. The magnitude response. The absolute value of JW is going to be equal to 1 divided by the square root of 2 squared plus 12.56 squared. And then we find, if you conduct this, we're going to find 0.078. And now the angle will be the negative of the inverse tangent of 12.56 divided by 2. Okay? Do you guys fully comprehend this? How we calculate the angle? Okay, the angle of this expression here. This is our reference expression. From this, we can calculate the magnitude response and the angle. And we find then the angle to be equal to 80.9 degrees. And then our response will be equal to 0.078 phase 80.9 degrees. Okay, this is our final response. And what does it mean? It means that the output is 7.8%. V0 is 7.8% of VI with a phase shift of 80.9 degrees at the frequency of 2 megahertz. At the frequency of 2 megahertz, the output is 7.8% of the input with a phase shift of 80.9 degrees. Okay, my friends, we have proved that this is a low-pass filter. At the C, the signal is not much attenuated, but as we increase the frequency to megahertz and even more, the output is going to be close to zero, regardless of the input. Alright, this is the frequency response of a circuit. We establish one magnitude here, and we don't vary the magnitude of the input. And we go increasing the frequency of the signal until we have a map of the output with respect to the input, how the circuit behaves as we vary the frequency of the input signal. Okay, my friends, this was the video that I wanted to make. I hope you guys enjoyed and learned from it. I am a teacher. If you want to book a lesson with me, use my WhatsApp number, guys. Goodbye.